For those of you who weren't able to attend the Albertus Institute seminar on the debate over nuclear energy in Scotland and energy justice, I've recorded this video. So I will cover an overview of the wider context, civil nuclear technology as it is today, the potential for new types of nuclear reactor designs and waste recycling technology, and I'll also touch briefly on the ethical dimension of nuclear power. So where to start with this wide-ranging topic in terms of energy, sustainability and justice in a Scottish context? A starting point is to ask, do we need nuclear power in Scotland? Nuclear energy is considered, of course, a low carbon technology, but Scotland also has lots of potential capacity for non-nuclear alternatives. Wind power, battery storage, expanding pumped hydro storage schemes, wave power, geothermal, energy from biomass, and even solar power. But something to highlight from the outset on any debate over nuclear energy is that most of our energy, in fact, comes from fossil fuels. Nuclear is, at the moment, a pretty small player in terms of total primary energy usage worldwide. A bit less than renewables, much less than the 84% of primary energy sourced from fossil fuels. Now, primary energy is not the same as electricity. If we think of total primary energy, this includes fossil fuels used for heating, for transport, for industry, and also for electricity production. So 84% globally from fossil fuels. And to try and visualize this, if we were to take all of the fossil fuels consumed every day around the world, all of the coal, all of the oil and the gas, and using our imagination, turn that into barrels of oil equivalent. And if we took all of that liquid oil equivalent, and if we thought of Niagara Falls on the US-Canadian border, if you replaced all the water with barrels of oil equivalent, it would take something like 5.5 hours for all the fossil fuel equivalent barrels of oil used in the world every day to pass through Niagara Falls. So that is a staggering amount of fossil fuels consumed every day. And if we're talking about reaching net zero by switching to electric systems, then logically this means a substantially increased consumption of electricity nationally. And it means the need for zero direct emission sources of high-grade heat for the economical production of alternatives to fossil fuels. So particularly in certain industries. These industries are also hard to decarbonize. One of the issues of concern with all of this is the sheer scale of change that is required. It's going to take a lot to scale up electrification. And there are certain industries, as mentioned, that are hard to switch from fossil fuels to a zero direct emission alternative. And there have been studies done indicating that if only renewable sources are used as part of a decarbonisation transition, the costs of mitigating carbon emissions will be higher, potentially much higher, than using renewables plus nuclear energy. And why is that exactly? Well, traditionally, we've had power sources like nuclear and coal, where the output is predictable. You could call this a kind of traditional grid setup. So these sources and others are usually termed base load supply. So historically, you had charts like this one showing base load, intermediate, and peaking. So peaking is referring to peak demand times. Now we just got rid of coal as a baseline supply of electricity, so the goalposts are shifting in a sense, and the old way of running a national grid just got more complicated and will continue to get more complicated. There are some that argue that renewable energy can provide a sort of base load, but renewables are fundamentally intermittent. And with the exception of geothermal energy, if you could ever make it work to generate baseload electricity, generally speaking, with renewable sources, the energy produced is not always produced when you need it. So it's challenging to have grid balancing, particularly when a higher proportion of generating capacity relies on renewable sources. So grid balancing in Scotland and the rest of the UK is usually achieved through dispatchable generating capacity. So pumped hydroelectric schemes are pretty good at achieving dispatchable quickly, and pumped hydro schemes such as Ben Cruachan are limited in capacity. Still decent capacity at 440 megawatt output, scheduled to be expanded to 1000 megawatts, that's a gigawatt, by 2030. So basically, schemes like this are trying to store excess renewable capacity to use it when it's needed. So you also have things like grid interconnectors, which help compensate for intermittency, but again, capacity is limited. So with the national grid, at the moment, it's largely natural gas generators that top up the grid when the wind isn't blowing and also supply peak time demand when it's required. And with natural gas prices reaching historic highs in 2022, this inevitably has pushed up the costs of generating electricity. Has this pushed people into fuel poverty and a cost of living crisis? Well, this is ultimately when it becomes a more immediate question relating to energy justice. Energy justice being the opposite of fuel poverty. That's one definition. I could go on and on about the details of the energy mix and trying to achieve storage with batteries like these ones, or the potential of geothermal energy, but basically the situation boils down to that including nuclear as part of a decarbonisation strategy will decrease the overall mitigation costs of achieving a net zero energy transition. And advanced nuclear technologies could bring further cost savings. And this is where the role of an ethical analysis starts to get interesting. That is, when we start considering new designs of civil nuclear technology. Before going on to new designs, it's worth explaining the currently available technology for civil nuclear power. We can term this Generation 2 or Generation 3 designs, such as this pair of pressurized water reactors under construction at Hinkley Point C. And you'll note the power output is pretty massive, 3,200 megawatts output. Something to mention is that this current nuclear technology has its origins in reactor designs for military purposes. Current reactor designs, like a pressurized water reactor, generally have their origins in reactors designed for powering nuclear submarines. And gas-cooled reactor designs, like TORNES, have their origins in producing plutonium for weapons production at wind scale. That's now known as Sellafield. So I wouldn't say this in itself makes the peaceful use of nuclear energy unethical, but the military origins of our current fleet of reactor designs needs to be recognised. So I'm sure that you'll agree that safety is something we value in relation to atomic energy. In terms of ethical values, safety is an ethical value. And over time, as civil nuclear reactors got bigger, more and more safety systems have been added and the designs were refined. And this is what makes the military origins of civil nuclear relevant, because it has become expensive to stick with the designs of a military origin and also scale them up, meanwhile ensuring nuclear safety. So you have this term of Generation 3 or Generation 3 Plus designs, like the Westinghouse AP1000. These are designs that are either under construction or can be approved for construction, say, over the next few years. So generally, that just means pressurized water reactors or boiling water reactors. Those are the currently available, currently deployed designs. Before I move on to new reactor designs, there are some general ethical objections to nuclear energy that should be noted. These have historically centered around several issues. So first of all, you have the very long time spans involved with the radioactive decay of nuclear waste, plus its high level of toxicity is of ethical concern. By long term, we really mean over 100,000 years. Furthermore, if something does go catastrophically wrong with a nuclear power plant, the magnitude of a worst case accident leaves potentially large areas of land uninhabitable. Furthermore, an objection would be that populations exposed to radioactive emissions are unable to control what happens to them. Ethically, increased radiation exposure risks for the general public and an inequity in the distribution of risk associated with nuclear energy is seen as an issue. There are justice concerns in relation to the nuclear fuel cycle and who is affected. That can cover everything from where uranium is sourced from all the way through to where disposal sites are identified. There are also concerns over the mechanisms of compensation in the event of a major accident. And furthermore, a link or a potential link between civil nuclear power and the use of reactors or reprocessing or recycling technology for military purposes is an ethical concern. That generally falls in the category of proliferation concerns. So these are all concerns that need to be considered. And a strong regulatory body and a system of environmental impact assessment help to allay at least some of these ethical concerns. There are, of course, some notable failures in nuclear safety. Chernobyl in 1986, Fukushima in 2011. I'm not going to go into more detail of historic nuclear accidents because that requires much more time for a forensic investigation. What I will move on to now are new designs for nuclear reactors. So there's something called the Generation 4 International Forum. And from about 2002, this forum has produced a vision for future designs of advanced nuclear reactor technology. And partly this was aimed at addressing the ethical concerns addressed previously, and also learning from mistakes of the past. So the four basic parameters were sustainability, including a minimization of nuclear waste and a reduced stewardship burden. Then there was economics, that is, coming up with reactor designs featuring advantages in terms of life cycle costs and reduced financial risk. Then there's a parameter of safety and reliability, which is designing for a low likelihood of core damage and eliminating the need for off-site emergency response. And then there's the parameter of proliferation resistance, which is to say ensuring civil nuclear power cannot be weaponized. The Generation 4 International Forum produced 6 generic conceptual designs of advanced nuclear reactors aimed at development from about 2030 onwards. And there are currently about 50 modular type reactor designs, all being developed by different reactor developers. These include molten salt reactors, advanced high temperature gas-cooled reactors, and also some more exotic designs. So an ideal fission reactor, we're talking about fission really rather than fusion reactors. The ideal fission reactor needs to be completely safe, where events like Chernobyl or Fukushima would be impossible. And ideally, there should be no movement of irradiated materials, there should be minimal waste arisings, and a reactor plus the entire fuel cycle should be cheaper overall than gas or coal, particularly for electricity production. We will never, of course, have an ideal fission reactor. But in having debates over the ethics of nuclear energy, this has led to innovation. There are, for instance, developers working on new designs for reactors which claim to be cheaper, safer, and produce less problematic waste than current designs. And some of these, but not all, will very likely become a commercial reality. There are quite a few developers of reactors working on molten salt related technology, and that cannot undergo a meltdown since the fuel is already a liquid. Other developers are working on helium-cooled reactors that are very safe and efficient. New types of reactors like this could be used for industrial purposes, requiring high temperatures. And new designs of either molten salt reactors or high-temperature gas reactors may be capable of achieving dispatchable electricity production from nuclear energy, probably using heat stores of molten salt. So the elephant in the room really is what to do with spent nuclear fuel once it's come out of a reactor. The first question to pose is it actually nuclear waste, or is spent nuclear fuel a potential resource that can be recycled? If we consider spent fuel as waste, then this means it needs to be disposed of, probably in deep geological repositories. And that brings in justice-related considerations like where would these repositories be located? What does it mean for communities who are going to be hosting spent nuclear fuel buried deep underground, particularly when the timescale of these projects could be at least decades, if not 100 years? And what happens if no disposal sites can actually be approved? Then there are the intergenerational justice concerns, that is, concerning the effect several generations from now. It's generally agreed that landing future generations with the task of managing nuclear waste is ethically problematic, to say the least. Another perspective is that what we call nuclear waste may be useful as fuel for reactors in the future. That is, assuming technology for recycling of spent nuclear fuel can be deployed. There are some pretty promising developments with electro-refining technologies, also known as pyroprocessing, which are very promising as a way of recycling spent nuclear fuel. Something not really talked about is the potential for a conflict between ethical values of justice, depending on your perspective, of an ethical value of conserving natural resources for future generations. So should we be permanently disposing of spent fuel, or for that matter, reactor-grade plutonium, when future generations may in fact need this leftover fissile material to meet their own energy needs? And that could be to run converter reactors, or indeed breeder reactors of some sort, which would tap into the potential energy resource of elements like thorium-232, which could potentially provide energy for thousands of years. Other ethical issues include concerns over the proliferation of nuclear weapons, and that is certainly something I'd say is important in terms of Generation 4 designs, and really should be given priority as being part of ethical consideration at design stage, but also in setting international standards. Non-proliferation as an ethical value may be in conflict with other values. So overall, quite an important point is there is an issue of how we prioritize values. There are, of course, ethical arguments in favor of nuclear energy. In 2022, philosophers of science and technology, Simon Friedrich and Martin Boudry, wrote a paper arguing that in relation to national energy policy, there is sometimes an ethical obligation to start or continue with a civil nuclear program, and that is based on the need to tackle climate change. And I would put it to you that Scotland would be included in this. There is an ethical obligation to develop an advanced nuclear program, given our history and given the sort of expertise that Scotland has in terms of the science and engineering needed to develop innovative nuclear technologies that address ethical concerns and also offer part of a solution to climate change. So what is there to take away from this brief overview? I would say that overall, in a debate over nuclear energy, there needs to be a use of proportionate reason in the debate in Scotland. So the basic issue is here that there is no such thing as an ideal fission reactor, and there will be trade-offs. So rather than a debate over whether we should have nuclear energy in Scotland, the real debate should be over which ethical values should be prioritised. And I think the term proportionate reason is a useful term to take away for future debates. And that is in part because there's never going to be an ideal energy technology that features zero negative impacts in terms of real-world applications. In pursuing a policy to phase out nuclear energy completely, this in itself expresses values and it has consequences for sustainability and for energy justice. And to conclude, I would say that it is through studying the ethics and debating the ethics of nuclear energy that we can better navigate the future of nuclear energy in Scotland.